Okay, here we go. Continuing week 8 office hours. We got that exam coming up tonight/tomorrow for the online portion and the in-person portion. And we got some concept questions. We got some voltaic cells, equilibrium. Then we've got some specific questions. We'll probably do the stuff in 4.1 first. Then we'll go to 7.1 to start talking about equilibrium, and then we'll wrap up with 7.2, 8.1 to talk about voltaic cells. So kind of following with the logic that we've done in class. Let's start with the 4.1 questions.
Let's see. So question,
Hey, come on in.
Question 2 it's pretty simple. It's like a reaction has delta R G standard is equal to negative 2150 kilojoules per mole. Which one of the following statements is true? And then it's like the reaction is spontaneous, the reaction is non-spontaneous, or under current conditions, the reaction is at equilibrium under current conditions, and then there's not enough information to know. And so the answer is like there's not enough information, but I'm just like I kind of just want to go through the logic of like realizing.
So what is it? So it was delta G naught or delta G?
Delta G naught.
Okay. And what were the different things that it said?
It's like, so the reaction is spontaneous under current conditions, the reaction is non-spontaneous under current conditions, the reaction is at equilibrium under current conditions, and there's not enough information to know. So I think just conceptually, or like going through it, like the logic, I'm not really 100% like about it, I think. Because I was like, my first instinct was to say that it's spontaneous because it's a negative delta G.
Yeah,
but
right.
But then it wasn't. So it's like there's not enough
So
information.
this is where spontaneous gets to be a weird word. Let's all scoot in. Let's get bags underneath desks and chairs so we can fit as many people as possible. There's another folding chair back behind the door there as well. So remember, delta G standard tells us specifically about the standard conditions of how something would proceed. So when it says something like spontaneous under current conditions, non-spontaneous under current conditions, cannot tell, equilibrium, what are the current conditions? Right? These things are really about delta G, not about delta G naught.
But isn't
right?
like delta G naught, isn't it just like standard conditions, so aren't the conditions known? So that's why I was kind of.
Well, so that's where you can get into like the actual nuanced definition of delta G naught. Like the actual delta G standard is from some like initial all products to some final all reactants, right? So delta G naught can be thought of as the sum of the n of delta G of formation of products minus the sum of the coefficients of delta G of formation reactants, right? So it's just this idea of what did we have at the beginning, what did we have at the end. And so this delta G tells us that it's going to be product favored, that it's going to proceed towards products. But unless we have some way that it's like, we don't really know enough to say whether it's going to be spontaneous or non-spontaneous because we don't have any Q information.
So how do we know? Okay, wait. So
right,
spontaneous
so
and non-spontaneous is only for non-standard delta G?
Well, so that is kind of more or less, right? So the term spontaneous, non-spontaneous is really a physics term, right? And it has to do with something that's going to happen as like a phenomena that's going to happen or a phenomena that's not going to happen. So without knowing how the chemical reaction is written down, not knowing like the initial conditions of it, we can't really say if it's spontaneous or non-spontaneous. We can say if it was set up at standard conditions, right? It essentially comes down to this defining of undercurrent conditions.
Because we don't know what the conditions are,
Yeah.
what current conditions are talking about.
Right. So
but for example, if it said under standard conditions, would we
then it would be different, right? So under current conditions is saying essentially some Q, which is where it gets us to delta G.
Okay. But
right.
So if it said standard, would the answer be that it's spontaneous?
Yeah, if we were going from standard conditions, right, then it would be from like 1 molarity, and we would be able to say that it's spontaneous, right? So this problem was really getting into the key terms vocabulary, 1 through 5. How many days have you been doing key terms vocabulary? Right, and so this is a lot of these like nuanced questions are really looking at what's the definition of spontaneous, what's the definition of a non-spontaneous, what's the definition of product favored, what's the definition of reactant favored, what's the definition towards products, what's the definition towards reactants. Because those 6 things refer to 6 different concepts. But in our heads, we're like, oh, spontaneous is towards products, product favored. We tend to clump those together, but they are not the same things.
Can you go over like different ones, or is that too much?
I mean, I can like read definitions.
It's just definitions.
Yeah,
Okay.
right. So I mean, and a lot of it's just in the language. Towards products is from current conditions. Come on in. There's still some space if you're willing to sit. If everyone can scooch in, get closer. Right. It's mostly in the language, right? Spontaneous, non-spontaneous is for as the process is already written down, is it going towards products, is it going towards reactants? For it to be spontaneous as written down, it needs to be going towards products. If we write the reverse reaction down, it needs to be going towards products still for it to be spontaneous, right? So it's just definitions, definitions, definitions.
Okay.
And I don't, with the number of things we have to do, I don't know if reading definitions is the best way to spend the time. That's part of, and I don't like doing that in class either, which is why I keep asking all of you to read key terms and definitions so much. Because if I spend the class going over key terms and definitions, because we do that some, but if I spend the entire class going over all the key terms and definitions, we just don't have enough time to do the harder problems that we really want to be getting to, that we really want to be working on together. So that's number 2, is just this idea of spontaneous, non-spontaneous, how that's working. There's still space in here, it's just people are being shy. So that was 4.1, number 2.
It covers number 5 too.
What's number 5 ask? Let's still talk about it.
It was saying like, basically just like, so if you had non-standard delta G is equal to 63 kilojoules per mole, and then the same like options, like what is it? And then so like now that you explained the first one, I understand like when it's saying like under current conditions, that's relating to Q.
Yeah.
And delta G is like regular delta, or delta G non-standard is relating to Q versus delta G standard is relating to K.
Right. So we can tell from, because delta G has that Q in it, we know that this 63 positive is relative to the equilibrium constant. So we've got some kind of initial condition in there. So we can tell that this is going to be non-spontaneous. From whatever conditions we have set up, this is going to be non-spontaneous. Cool. So that's number 5. Number 13?
Okay. It's kind of similar, but I kind of just wanted to ask about the logic of like going through it. So like for a reaction, Q and KEQ are both very small values, but Q is smaller than KEQ. Which of the following statements is true?
Okay, hold on a second. Let's get that down. So we've got Q is less than 1, KEQ is less than 1, but which one was smaller?
But Q is smaller than KEQ.
KEQ is bigger than Q. Q is smaller?
And then which one of the following statements is true? The reaction is spontaneous. It's just the same.
Right, and we can think about this, again, in terms of those 6 different ideas. Yeah. Just from this. Q being less than 1 doesn't really tell us much. It tells us where we're starting. KEQ being less than 1 can tell us that this is going to end up being something that is reactant favored, but not which direction we're going to go, right? KEQ is going to be some products at equilibrium.
Would you kind of like...
over reactants at equilibrium. And I can tell if KEQ is less than 1, my product's value has to be smaller than my reactant's value, so I'm going to end up being reactant favored. I'm going to have more than half of the reactants. So that's what the KEQ tells us, but it doesn't tell us which direction we're going to go in our reaction, because I don't know where we're starting. Just from the KEQ, I don't know where we're starting. But then I know that my KEQ is bigger than my Q. So even though they're both small, even though I'm reactant favored from this tells me I'm reactant favored. This KEQ.
If the products are less than the reactants, then wouldn't the reaction go towards the products?
Not necessarily, right? This is where it will end up after it runs. But where do we start? What's our Q value? It's always this comparison of the two. It's always this thing that tells us whether we're going towards or away from something. It's this telling us where we would end up eventually. This tells us how we get to where we end up. Are we going uphill or are we going downhill? Are you going downhill to the south, downhill to the east, downhill to the west, like where, right? So we need that kind of comparative knowledge. So this tells us KEQ is bigger than Q. So this tells me that even though this is going to be a reactant favored thing, this bit of information tells me I'm going to go towards product still. Because my KEQ is bigger, that means my Q doesn't have enough products yet. So even though it's reactant favored, it's still going to go towards products. And that's how those two things are subtly different, even though we tend to group them in our heads. Question?
And because it's going towards products, could you say that delta G, just delta G, is negative?
Yeah.
Okay. Oh, could you make any assumption about delta G naught, or is that also?
Yeah, because we've got our KEQ is less than 1.
Oh, right.
So we can do something about delta G naught as well, right? We can plug it into our equation where we've got negative RT ln KEQ, natural log of it. Yeah, so it's going to end up with a positive delta G naught. So we can tell all of those things. If you're willing to scrunch in, there's space, but.
Yeah, there's.
Okay, so that was number 13, right? All again around those 6 different phrases: spontaneous, non-spontaneous, product favored, reactant favored, towards products, towards reactants. Which is kind of the stuff we were doing. Some of that was on the first exam, but we still needed it as we went to the second exam. Number 19?
Yeah, so this question is...
Is it a continuation idea, or can I erase?
I think you can erase.
Is that okay with everyone?
Is it number 5 or 13?
This is number 13, so 1, 5, 13. Okay, number 19. I'm going to go ahead and erase the board. No one's stopping me. Okay. Number 19. What do we got?
A solution of an unknown substance in an unknown solvent boiled at a temperature 5.65 degrees Celsius higher than the boiling point of the pure solvent and froze at a temperature of 10.9 degrees Celsius lower than the freezing point of the pure solvent. The value of Kf for the mystery solvent is 12.3 degrees Celsius kilograms per mole. What is the Kb for the mystery solvent?
What was the Kf value?
The value of Kf for the mystery solvent is 12.3 degrees Celsius kilograms per mole. What is Kb for the mystery solvent?
Wait, degrees Celsius kilograms per mole?
Yes.
Okay. Oh, right. Should that be a fraction, or should it be like that?
Oh, sorry. It should be degrees Celsius times kilograms per mole.
Okay, there we go. I was like, I knew I had something wrong. Right. Okay, because kilograms per mole, moles per kilogram, that's like 1 over molality. Okay, that makes sense. So, what the heck do we do with this problem?
I think it's like,
First thing we do with all of our problems is we look for hints in the text that tell us what kind of thing we're looking at, right? I've got this increase in boiling point, this decrease in freezing point. I've got some change in my boiling point, some change in my freezing point. So I'm going to be using delta TB equals I, KB, molality, delta TF equals I, KF, molality. And I have to use the context of the problem to kind of give me some information about what's going on. Always look for that context. Again, this is another reason why key terms and vocabulary become so useful and so powerful. Right? Once I set the problem up, y'all can click-clack in your calculators, no problem. Right? You're all great at math. You're great at algebra. You're great at, probably calculus even. And we're just doing additions and subtractions, multiplications, divisions, a couple exponents. Right? We're not really doing any hard math. The difficulty in all of this is how does the language tell us what math we're doing to explain the phenomena we're considering? That's the real difficulty. And that's where key terms and vocabulary, again, become really powerful. After I identify the fact that I've got this equation these two equations that I'm working with from the context of the problem, I can notice I've got delta TB, I've got delta TF, so I've got those two numbers. I've got KF. It's the same solution, so IM is essentially going to become my unknown variable. So I can rewrite this. I've got the KF, so I can rewrite this to be delta TF divided by I molality is equal to, sorry, that's not how I wanted to do that. Delta TF divided by KF is equal to I times molality. Since it's the same solution twice, once I solve for that I times M as a variable, I can take that and I can just plug it back in there. So we're going to end up with an equation. If I do all of the substitutions, I'm going to get delta TB over I molality is equal to KB, right? It's asking me to solve for KB. That was the question I didn't write down. Right, what's my KB? Question.
And you can plug in the IM from the TF to the TB because it's the same concentration.
Same solution, right? Is one solution that froze at one thing, melted at, or boiled at another thing. So I can do another substitution, and I can get delta TB divided by delta TF over KF is equal to KB. I got that number, I got that number, I got that number. Solve. Right, mathematically, it's going to be 56.5 divided by 10.9. That's going to be a value of about 5.65. 10.9 divided by, or 5.65 divided by 10.9. It's going to be about a half. Times 12 is going to be about 6. The answer is going to be about 6.
What is molality again?
So molality, as a reminder of what molality is, right? So molality is essentially a new unit of concentration. Right, and it's moles of solute per kilogram of solvent. Right, and the reason we did this is because versus molarity, which is moles of solute per liter solution, when we're dealing with these situations where the temperature is going really high and really low, volume's going to change, right? There's going to be expansion and contraction. Liquids expand, most liquids expand when they heat up. So if we were using total volume of solution, that would actually change as we heat things up and cool things off. So temperature, if we're using molarity, as long as we're not changing the temperature very much, we're fine. But if we're using molarity and we're changing the temperature a lot, like going to the boiling point, going to the freezing point, that will change the concentration. The concentration will become a variable as temperature changes over large ranges. And so it's not that great. So molality became this other unit that we could use for concentration that goes based off of mass rather than volume. And that's going to have some benefits to it. It also simplifies the units. Rather than doing kilogram of solution, it does kilogram of solvent. So it also has some industrial practical systems where I can just measure the mass of my solvent, dump in the right amount of solute, and that's it. I'm done. Right? So in terms of mixing and making solutions, order of operations doesn't matter. Right? if you remember the Gibbs lab we did where you had the potassium nitrate and you had to get the total volume after water was added, right? You added what, like 9 milliliters of water to like 5 grams of potassium nitrate, and the total volume ended up wasn't 9. It wasn't 9 plus 5. It ended up being like 12 milliliters, 16 milliliters. I can't remember where it was. But that was because the solid also took a volume. If we did that lab in units of molality, it would have actually been a little bit easier in terms of the mixing, because that final total volume wouldn't have mattered. We wouldn't have had to do like a density calculation or anything. We could have just said 9 milliliters of water is 9 grams, 5 grams of potassium nitrate is a certain number of moles. Doesn't matter what the total volume is. I can just tell from the way I put it together. So it has some practical uses as well. Do I need to crunch through the numbers, or do you all kind of get the important part of the key terms, point to the equations, identify which variables I have, which variables I don't know, do some rearrangement? But the important chemistry step is key terms pointing to phenomena, pointing to equations. Question?
The I is the ionic charges, right?
It's the Van Hoff factor.
Okay, yeah.
Right, so the Van Hoff factor, if we're doing ideal Van Hoff factor, that would be a whole number. It'd be 1, 2, 3, 4, depending on how many ions, how many things are going into solution. The boiling point freezing, the boiling point elevation and freezing point depression are both entropic phenomena, right? So they're happening not because of any chemical species, but just because the entropy is changing in different ways.
In this situation, we don't know like the actual like Van Hoff number
Nope.
because we're not given like any.
Nope. And we didn't need to know it, right? We can just
group them together.
We can just group them together. It would be essentially like, or you could say instead of grouping it together, it kind of cancels out, right? We essentially, by rearranging, we can cancel out molality and molarity through the substitution process. Sorry, molality and Van Hoff factor. There's no molarity.
And the Van Hoff factor, like the ideal one, is how many like things it can break up into, right?
Yeah.
Okay.
Right, covalent compounds, the ideal Van Hoff factor is 1, because it shouldn't break up, it should just be 1 particle going in. Something like sodium chloride would be a Van Hoff factor of 2, because in an aqueous solution, we always did ours for water, right? If we were doing this in some other weird solvent, it'd get weird. But we're doing it in water, so that Van Hoff factor, it would split into sodium pluses and Cl minuses. So that would be 2. And that would be that would have a bigger impact on the entropic effect, so that's why we need the Van Hoff factor there. It's probably not actually going to be perfectly 2, because water molecules are going to arrange around the sodium, they're going to arrange around the chloride, and we're probably going to see something a little bit less than 2. But ideally it would be 2. Other questions? Okay. So for those of you, quite a few who came in after we got started, I am recording this if you missed the earlier questions. These are the problems we have set to go on. We had some 4.1 questions. We've got 7.1, 7.2. We're also going to talk conceptually about voltaic cells and equilibrium, which is, I think, what we're getting to next with 7.1. So if you've got questions that go along with 7.1 or 7.2, feel free to shout them out. We can throw them on the board. Or, as you've seen, as you come up with questions for the thing we're talking about, just ask, and we'll just kind of work it together. Yeah?
Can I do 2 quiz questions from quiz 5?
Yeah. Which numbers were they? And were they more voltaic related or equilibrium related? Or were they like throwback questions?
No, I don't think they were throwback questions.
You know which ones those were. Hopefully, I haven't checked yet. Did everyone get them right? I hope. Okay.
It was
I'm gonna erase this while you're getting that together.
like one of them was like molar concentrations of cation and anion.
Okay, so that's an equilibrium question. Which number was it?
Number 2. And then the other one was number 3.
Okay. Yeah, we'll look at those. I think they're going to be more equilibrium related. Was the number 3 also equilibrium related? Yeah, yours?
The equilibrium one I had was number 7 and 6.1 actually.
Oh, 6.1.
Yeah, but then there was also another one from 7.1. It was number 23. And I think that's kind of like the Liaison.
The shot liaison as well. Cool.
Yeah.
I had a question about 18 and 20 on 7.1.
Okay.
18.
18 and 20, and that's voltaic cells?
Yeah.
Okay, so let's do 6.1, then we'll do the quiz questions, and we'll talk a little bit more generally about equilibrium, and then I think we'll be ready to shift over to voltaic cells conversations. So, starting with 6.1, number 7. Which one is it? Oh, it's that one. Okay, so consider the reaction, consider the 4 reactions, let's call them A, B, C, and D. Use the evidence below to find the delta H and delta S for each one. Okay, this is a great kind of introduction to equilibrium questions. So I'm just going to do 2 of them. I'm going to do A and C. And so we'll look at how A and C behave, because these go nicely. Maybe I should do all of them. Right, so we've got KEQ. Well, let's write down what this is. We're looking at 6.1, number 7. We've got KEQ greater than 1 at all temps. And let's go ahead and talk about what that means by itself first. We'll go through B, C, and D. I think by the time we get to, I'll do A and D together because I think they go well together. And at that point, hopefully you can do the rest. So 2 things we know. This is asking us to find delta H's and delta S's for the reaction based on this scant information if KEQ is greater than 1 at all temps. And for me, this is too vague, right? I'm like, okay, first thing I think of is okay, I know that KEQ relates to delta H and delta S. We got negative RT ln KEQ is equal to delta H minus T delta S. But if I'm being honest, this is too much at once for me to think about. Right? This is like, it's too much for me to think about all at once. So I'm going to break it into 2 steps. I'm going to break it into delta G standard is equal to negative RT ln KEQ. And delta G standard is equal to delta H minus T delta S. So in this situation, when I have it broken up, I can take this thing and I can break it into these 2 parts. It allows me to kind of compartmentalize my thinking a little bit. So KEQ greater than 1 means that's going to be positive, delta G is going to be negative. So from the fact that KEQ is greater than 1, I can tell delta G standard is going to be less than 0, right? That's to say it's going to be negative. Now, it's going to be negative at all temperatures. So I consider 2 extremes. I consider an ultra low temperature, like 0 Kelvin. I consider an ultra high temperature, like 1 billion Kelvin. So if I'm at an ultra low temperature, like 0 Kelvin, if that would essentially say this term goes away, and I just have delta G equals delta H. So if I'm at a low temperature, but I know delta G still has to be negative, that tells me about my delta H. Right? If I want delta G to be negative at all temperatures, that means at these ultra low temperatures, delta H also has to be less than 0. Delta H also has to be, I almost wrote X. Delta H also has to be negative, because ultra low temperatures, that whole thing goes away, and I just have delta G equals delta H. They both must be negative. Okay. Then I go to really high temperature. I go to approximately like, right, I go to like 100 billion trillion Kelvin, whatever, right? The point is, at 100 billion trillion Kelvin, this T delta S term, I mean, delta H is not going to be that big, right? 100 billion trillion Kelvin, this negative T delta S term is going to completely dominate. So if delta G is negative at 100 billion trillion Kelvin, that means this negative T delta S term must be negative at that really high value. So that means delta S has to be greater than 0. Delta S has to be positive at that really high temperature. Right? And so essentially what we're doing with temperature is we're just turning on and off each term. Low temperature, high temperature. Low temperature, high temperature. And that's kind of how we go through that consideration. What about a temperature someplace in the middle? I have no idea. But, oh, actually, no, I do, because delta G is always negative. So it's got to be negative still. Delta H is going to be negative, delta S is going to be positive, but that's where thinking about the extremes helps out. Let's do it for another one. I'll let you pick. Do you want to do B, C, or D?
C, sure.
Let's try C. Okay, so I'm going to erase this part down here because this is what we're going to redo. I'm going to leave that bit in blue. We're going to do C. So for C, we have KEQ is greater than 1 at low temp. KEQ is less than 1 at high temp. Did you have any specific questions you wanted me to address still?
I do, but like it's fine because you're going over like quiz stuff.
Okay,
I have,
was
like,
it quiz
quizzes
questions?
from my teacher.
Oh,
I
that's
wanted to
right.
go
Oh,
over
drat.
that.
Okay. Come back at 4.
I have an appointment.
Okay. Sorry about that.
That's good. Thank you though.
Okay. Okay. Making sure I got this right. KQ is less than 1 at high. Oh, I got it flipped. KEQ is greater than 1 at low temp. Oh no, I got it right. KEQ is greater than 1 at low temp. KEQ is less than 1 at high temp. Okay. Perfect. Okay, so this is what we're looking at. And I do the same type of logic, right? So if KEQ is greater than 1, that is going to be a negative delta G. Delta G is negative. At low temp, I'm going to have that term disappear. That means delta H must also be negative. Because at low temp, that T delta S goes away, and I just have delta G equals delta H, so they both must have the same sign. Then I go to high temp. Oh, that's awkward. At high temp, KEQ is less than 1, so I'm going to have a natural log of like 0.01, that's going to be negative. That's going to be delta G is positive. And at that high temp, this delta H term is essentially going to be turned off. And so it's just delta G equals negative T delta S. So in order for delta G to be positive at those high temperatures, delta S has to be negative. So that we have the negatives cancel out and it becomes positive. So delta S must be negative. So delta G is switching from positive to negative depending on the temperature. That's why KEQ is flipping. And that allows me to figure out delta H and delta S. They both must be negative. So it's just kind of like useful extremes. Extreme high temp, extreme low temp. That was 6.1, number 7. And this starts to get us to thinking about equilibrium. What does this KEQ value being big or small mean? We can see that it changes with temperature. How does it change with temperature? What does it mean for it to be changing with temperature? And what can we do with equilibrium? Should I do some kind of conceptual work with equilibrium, or should we just do the set problems? Okay, I'll do some problems, and then we'll get kind of concept work on it as we go. Right? I'll do a little bit of concept work first. We started with these thermodynamic ideas. Thermodynamically, we know that there's some energy being released from the bonds, and there's something associated with how that energy is organizing. That's the entropy idea. It's expensive to keep energy dense. Energy tends to spread out, and that's what this T delta S term is trying to get at, is this idea of energy dissipation. This first equation is the delta G naught equals RT, negative RT ln KEQ. That's where we start to say, okay, we want to think about this in terms of some chemical system. We want to think about this not in terms of like physics and thermodynamics. Well, in conjunction with physics and thermodynamics, we want to start thinking, how can I apply this to a chemical reaction? And that's where this idea of KEQ and Q come in. I'm going to erase all of this if that's okay. Right? And this is where that idea of KEQ and Q come in, where both of these are just parameters to track our reaction, right? Q becomes this thing that tells us at any point how much products do we have, how much reactants do we have. And KEQ is going to be the amount of products we have at the equilibrium point for the reactants we have at the equilibrium point. The KEQ is a single value for a given reaction at a temperature, and it's going to be that energy minimization. It's going to be the balance between delta H and delta S between the products and reactants that makes so essentially the reaction appears to stop. That's going to be that equilibrium point. Technically, it's still going backwards and forwards, but it's going backwards just as much as it's going forwards. So anytime we look at it, it looks like nothing has changed. Even though there's still some flux there, it looks like nothing has changed. And so we can use this to track where we are versus where we're going to end up. This also brings back those ideas of product favored, reactant favored, towards products, towards reactants, those different ideas. We don't really talk about spontaneous or non-spontaneous anymore. But we still have those different ideas of product favored, reactant favored, towards products, towards reactants. And with that in mind, we can start to look at some of these. Was the 7.1 questions equilibrium problems or was it quiz?
They were equilibrium.
Was that?
I think they were equilibrium and then like you changed it.
Okay, so if we're looking at 7.1, we refer to the reaction, assume the reaction is already at equilibrium in a single beaker. So this gets us to the Chatelier principle. We're already at equilibrium. Okay, so if we're at equilibrium, okay. So you got the first thing. You did something funny with the first thing. Where'd you get that delta G value? So if we're at equilibrium, there's a problem that's asking us to solve for, the first part is asking us to solve for delta G. Right? Not delta G standard, just delta G. And we know this is going to be RT ln Q over KEQ. But if we're at equilibrium, we've got our three different possibilities when we're looking at Q and KEQ. We can have KEQ. I always like to do KEQ first, but we have KEQ greater than Q, KEQ equal to Q, KEQ less than Q. And those are the three possibilities that's going to cover all of the numbers that we could potentially have. If we're at equilibrium, we're at this point where KEQ and Q are equal to each other. If Q and KEQ are equal to each other, we're going to have delta G equals RT natural log of 1. What's the natural log of 1? Right? So our delta G is going to be equal to 0 in that case. That might be the only thing you had wrong on it.
Oh, okay.
I haven't looked at the rest of the questions, but that's kind of the first, I just saw that right away. I was like, where'd you get that number? Right? Because it specifically said we are at equilibrium, we're at delta G equals 0. In terms of our Gibbs plots, right, so if we did a Gibbs plot, I have no idea what this plot would look like yet, but it doesn't matter, right? Let's say this is what our plot looks like. We're going to be at this point, right? And if we're at the bottom of the curve, the slope is 0, and delta G, non-standard, is kind of like the slope along the curve. It could be going that way, but we're at the flat part. So we end up with like a 0 value for delta G. Our delta G standard still has a value, because delta G standard is a measure of energy differences from a standard condition. Delta G is saying we're at equilibrium, our KEQ and our Q are the same, reaction doesn't happen, right? There's essentially no energy to push the reaction anymore when you're at equilibrium. Now what it does is it says, let's mess with the equilibrium. We're at equilibrium, and we're going to push the reaction away from equilibrium and see how nature responds. This is called Le Chatelier's principle. Essentially what Le Chatelier's principle says is, key terms definitions, if a system is at equilibrium, and we disturb it away from equilibrium, it will tend back towards equilibrium. So if we increase the amount of products, it should shift towards reactants. If we increase the amount of reactants, it should shift towards products. That's how we think about it in chemical sense. But Le Chatelier's principle applies to a lot of other ideas as well.
I'm kind of confused why you're using the equation of Q over KEQ, like, why are you... Couldn't you just do RT ln K?
No, that would get us delta G standard. The problem was specifically asking for delta G non-standard.
So that may have been what I was trying to solve for.
Oh, you were trying to solve for
Yeah.
delta G standard?
I
Where you've
still
got
probably
a
wrong,
delta
but-
H, no delta S. Did you go into the textbook and calculate delta S from the standard table?
No.
Okay.
I don't
Because you could try to figure out what the equilibrium constant is. It gives us the delta H. Delta H alone is not enough for us to figure out delta S or delta G standard. But if we pulled up the textbook, we could try to calculate delta G standard and delta S standard. The problem is specifically asking for delta G. So it's asking us to use this equation.
Okay, but then it says already at equilibrium, so how are you just assuming that?
If we're already at equilibrium, Q is equal to KEQ.
Okay.
Right? We're in this condition. KEQ is equal to Q. That's why I get a value of 1 there, because KEQ divided by KEQ is 1.
I think what I tried to do was like use the cell potential.
Oh, wild. That would get you delta G standard, not delta G,
Yeah.
because it's the standard cell potential. Interesting way to approach it. Also possible. You could still get to the right idea that way, but not what it was asking
Yeah.
for. So we throw in copper solid to the reaction mixture. Do solids participate in the equilibriums? Not really, so that's not going to do anything. We add copper 2 to the reaction mixture. Copper 2 is a reactant. Did you get your question answered?
No.
Is it
but
on
I-
the board though?
No, but I have.
Which question was it?
It was more of a conceptual question.
What was it? I'll still get it on the video and you can watch.
It was so regarding like the video from Monday, you wrote something about delta G being greater than 0, but that it was reactant favored. But I thought it was product favored, so.
Okay.
Oh, but it's delta G standard, I think.
Delta G standard greater than 0. Then I might have made it. Was that in the?
It
That's-
was in the video on Monday, I think, or Tuesday. It was one of those days.
I'll have to think about that. I'll take a look at it. Okay. So if we put more reactants in, right? So we were at equilibrium. We put more reactants in. That's going to send us up this way. Now we have to go back towards products to get back to equilibrium. So that should increase the amount of copper, decrease the amount of iron, right? Because we've got to react more to get back to equilibrium. Then we add iron 2 ions. That's adding reactants. So adding iron 2 ions would be like disturbing it up this way. And now we've got to go back towards reactants to get it. So that's going to increase the amount of iron, decrease the amount of copper. And so that's kind of the logic we go through. I really like these plots for thinking about that. Add water to the reaction mixture, raise the temperature. If we add water, okay, adding water is actually probably the most interesting of these. So if we add water, we're going to be changing the concentration of the products and the reactants evenly, but they don't evenly affect Q, right? If I'm looking at my balanced chemical reaction, I'm going to do products over reactants. Again, this is, sorry, I should have written this down. This is 7.1, number 23, if you want to look along. So for this setup, products over reactants is going to be maybe 3 plus squared divided by Cu2 plus cubed. So let's say we add enough water that we cut the concentrations in half. Right, so my concentration goes to half. That's going to be similar to saying I've got, like, let's say they were all 1 molarities for fun, and then we go to 0.5 molarities, right? That's going to give me 0.5 squared divided by 0.5 cubed. Because there's this cubed on bottom, the dilution is going to have a bigger effect on the reactants than it has on the products. And so that's going to effectively make it seem like the products are more concentrated than the products. Because they're not, if it was an even like squared, no effect, right? They're both squared, it doesn't change anything when you add water. But in this situation, where it's a 2 to 3 mole ratio, that concentration change is going to affect the Q value unevenly. And it's going to make the Q value, since it's 0.5 cubed on bottom, that's going to make our Q, because it's a smaller number on bottom, that's going to make our Q value bigger. And so that a Q value getting bigger is like moving this direction. Right? So we're going to disturb the equilibrium, and then nature's going to come back at us and be like, nope, I want to go back. So we're going to disturb equilibrium towards a larger Q value, and then we're going to go back towards reactants. That's a weird one. Right, so that is the mass of iron decreases. Oh, it should be the mass of iron increasing in that case, right? Because we want to get back to making more iron.
So,
and increasing our copper concentration, right, to get back to equilibrium.
you just like think about it, like because you're like the Q value increases, it's going this way, so that means it's going towards like products.
We've disturbed it towards products,
and it's
going to go back toward, and it's going to readjust back to the bottom.
Okay.
So that's Le Chatelier's principle in a nutshell. Is if you go up the slope, nature comes back down the slope.
Yeah.
If you go up the slope this way, nature comes back down the slope. And that's pretty much Le Chatelier's principle. The last part of this is we're doing this with temperature. Notice this is an exothermic reaction. So that means heat is essentially a product. So if we increase the temperature, that would be like adding products. If we add products, it's going to go back towards reactants.
If it was endothermic, would that make heat not a product?
That would make heat a reactant.
How does that work? That like if it's exothermic, it's a. Oh wait, I think I understand.
Okay. Cool. So that's Le Chatelier's principle. Is just you disturb, nature comes back. You disturb, nature comes back. Question.
Really quickly, just about what you were last saying. So if it's exothermic, heat is a product. So if you increase the heat, the temperature, then
It's
it goes
like-
back to react.
Yeah, because there's like
Right.
adding a
Adding
product in
products.
that
Okay.
case. Question here and then there.
For the H2O, you're saying that it ends up being more products than reactants, and
So for the H2O, we're going to dilute the products and the reactants by the same factor, but then the reactants get cubed. So that's going to make the Q value get bigger.
Okay.
And that bigger Q value means we've disturbed towards a bigger Q value, and it's got to shift back.
Okay. Is there like? Oh, sorry.
Is there a question over there?
There was a question on the homework like a bit ago that also like it was like what'll happen to the equilibrium if you add pressure.
Yeah, so that's going to be a similar thing where it's going to be like gas phase, and it's increasing, decreasing pressure is like increasing or decreasing the concentration of a gas. So you get the same concentration idea. Increasing pressure increases concentration of the gas, and you get the same thing where if it's even mole ratios, no effect, but if there's a difference in mole ratios, you have some effect. Did you get your?
Yeah.
Cool, okay. Other questions about this? Did you have one?
Oh yeah, I had something related. Is there any like in a situation, right? They add more water, and so it dilutes the like concentrations.
Mm-hmm.
Is there situations where it could like increase both of the concentrations? Do you know what I mean?
That would be like evaporating water out with a non-volatile solute. You could effectively like get rid of the water without, and that's the only way
And then
you
it's
can.
just the same thing, except instead of it decreasing, it's just increasing.
Yep.
And we think about
Yep.
that.
Yep. Exactly.
Appreciate it.
Less common, but still possible, because usually to get the water out, you usually have to heat it or boil it somehow. You can't like scoop the water out without getting it out. So it's more complicated, but theoretically, right? Dumping water on top of something that's already there, easy to do.
Yeah.
Other questions? Okay, so we can start to see how all of our equilibrium ideas start to tie together, right? We kind of get away from the delta H's and delta S's as we go to this idea of just keeping track of our chemical reaction. Now, the reason this keeping track of the chemical reaction works is because of our enthalpies and entropies, because of our delta H's and delta S's. That's the energy that drives this towards products or towards reactants, or like tells us where the bottom of the curve is all of that thermodynamic information, right? If we didn't have entropy, this graph would just be a straight line, and it wouldn't make any sense. It would just be like all one direction or all the other direction, right? You wouldn't really have anything else. But by having enthalpy and entropy, right, if you didn't want any entropy, you'd essentially have to say things aren't mixing while the reaction is happening. So stuff would have to, like your reactants would have to leave the reactants beaker and go into a products beaker so they're not mixed. Just not possible. It just doesn't make sense. So with entropy there, we end up with this little like swoopy curve. And that swoopy curve tells us how the reaction proceeds. And now we've got this minimum energy that the reaction is always going to tend towards. That's going to be the right balance between the products and the reactants, energetically. Let's keep going. And that's the main thing with the starting point of how we think about equilibrium. I'm hoping we've got some equilibrium calculations. I know we got that from quiz 5. But what about 18 and 20? Are those equilibrium calculations? I'm going to erase this as well.
Yeah.
Okay, let's do some I'm going to leave this stuff up here. What is number 18? So we're looking at 7.1. Number 18.
Actually, this is about predicting E cell, but it's
Oh, let's switch to quiz 5 where we've got some of those equilibrium problems. And then we'll jump back to 7.1, 7.2, 8.1. So let's look at quiz. Who else was asking about quiz 5? Quiz 5? Mm-hmm. Let's. What did you have for your quiz 5 number 2? Because you will all have potentially different random values and different random problems for the quizzes. So I'm not going to do all of the variations. There's too many, but we'll just do your quiz 5 number 2.
Okay. You know that for the ionic compound FeOH3, the KSP is 4 times 10 to the negative 28. What is the molar concentration of the cation Fe3+ and anion OH- in a saturated solution of FeOH3 at 25 degrees?
Okay. Key terms in vocabulary. What tells us what we're going to do in this problem?
That it's a saturated solution.
It's a saturated solution. It doesn't say anything else is there, so I'm going to assume it's a saturated solution in water. So, come on in. So, what am I going to set up in order to solve this problem? Equilibrium, saturated, equilibrium table. I'm going to set this up as FeOH3 solid goes to Fe3 plus 3 OH minus aqueous. I'm going to have some init, some change, some equilibrium, right? So I have my initial conditions. I'm not going to worry about the solid because the solid's not participating in the solution's equilibrium. I'm just focusing on the solution and the ions in the solution. And I'm doing a saturated solution in water, so I know I'm going to have these initial values of 0. I'm tossing iron hydroxide into a beaker of water. And I say, okay, this is obviously not at equilibrium. My Q value is equal to 0, so I know that this has to go towards products at least a little bit, probably a very little bit with this K value. But it has to go towards products at least a little bit. How much? I'm just going to use some value X. Right? For every iron hydroxide that falls apart, I get 1x there. I get 3 x's here because it's a 1 to 3 mole ratio. Every 1 iron is going to be 3 hydroxides. I do 0 plus x. I don't have to worry about, we're not doing any x's smalls or anything like that. There's nothing there. So I'm going to get x. I'm going to get 3x. I'm going to get my equilibrium expression is going to be iron 3 plus. Right, times OH minus cubed. And these equilibrium expressions were kind of a weird thing. Right? They do relate to the fact, so I end up with 3 hydroxides. This would be like iron concentration times hydroxide concentration times hydroxide concentration times hydroxide concentration. That molar coefficient of 3 tells me I have to take the bumping, the kinetic energy, the energies of 3 hydroxides into account. The 3 here is stoichiometry. The 3 here is thermodynamics. So I have to take both of those into account. Then I can, and was it just 4? Did I miss any numbers? Was it just 4.0 times 10 to the minus 28?
Yeah.
Okay, so now I can plug in my different values. 4.0 times 10 to the minus 28 is equal to x times 3x cubed. Same, is that what you did?
I think so. I don't know where my work is somewhere.
Oh, bummer. Okay. I will tell you the most common mistake I make at this point, which is embarrassing. I do this as 9x to the 4th. Because I do 3 times 3 is 9.
Yeah, I probably did
But
something like that.
it's 3 cubed. It's 27 x to the 4th. I'm recording this, so hopefully no one makes fun of me on YouTube. But I've actually made that mistake in an answer key. And like only 3 students got the problem right. And I was like, something's wrong here. Like my best students got the problem wrong. And I took like 20 minutes to find the mistake. And I did it, and I was like, no, did these 3 students really do better than everyone else? And then I was like, oh wait, no. And then it was like out of 48 students, and it turned out that like 35 students got it right, and those 3 students who got it right did not get it right. Womp womp. So let's go ahead and solve for x. We got 4 times 10 to the minus 28 divided by 27, not 9. To the power. Now, I use one of these simple little calculators, and I always mess up my power of things when I try to do power of a quarter. So I just do to the power of 0.25. Right, because I got to take a 4th root, so that's going to be like 1/4. Oh, yeah, to the power of 0.25. And another mistake that can happen is if you're using one of these simple calculators, you get these like string rounding issues. And so I always put it into scientific notation. So it just told me 6.000006 when it's actually 6.2 times 10 to the minus 8. And that's a particular problem when you have numbers that are on the order of minus 8 or minus 9. Your calculators won't auto switch to scientific for these simple ones. And it'll do like some funky rounding for you. So I calculate x is equal to 6.2 times 10 to the minus 8. That will be my iron concentration, right? Because my iron concentration is just 1x, that's my iron concentration. Question?
If you have like an equilibrium problem and it's like an aqueous plus solid leads to like aqueous or whatever, then it tells you like the aqueous concentration and then like the grams of the solid. Is that just saying like there's excess of the solid?
Usually, yes.
Okay.
There's a version of the problem that's not going to be on the exam. I don't think we really do it this quarter. There's a version of that problem where you can figure out how much solid is left. But I don't do that until 3rd quarter chemistry.
Okay.
Question?
But giving the information that the solid doesn't matter because it doesn't.
As long as there's enough, right? Right, so the place where that amount of solid could become important is if it was milligrams or micrograms of solid. You might have more dissolve. You might have all of it dissolved before you get to saturation. So all that matters for us is there's enough solid present that we hit saturation. And since we're always doing this for small KSP values, it doesn't really matter. Let me give you an example of where it would matter. If I said, oh, we've got a beaker of 200 milliliters of water and we put 3 grams of sodium chloride into solution, what's the saturation of sodium chloride? 3 grams isn't enough to saturate a sodium chloride solution because the KSP value is very large. So that 3 grams would create a whole problem. We'd want to do it for like, now if I said you do it with like 40 grams of sodium chloride, now you're saturating the solution, I think. Sodium chloride is really soluble, right? But the point is there's always enough solid present. We can, again, we don't do this until next quarter, but we can actually ask, do we reach the saturation point with that amount of solid? And kind of do a combination of equilibrium and some stoichiometry together. But we don't do that till third quarter. But that's why it gives you the amount of solid, is because it's enough to say, like, there's enough solid. Now what happens?
Wait, so then for the problem, like a problem like this, we talked about this last office hours where if there's a concentration on both sides, you have to find the Q value, right, before you...
Yeah, let's do an example with concentration on both sides, because it'll never be a solubility problem like this, right? That's got to be like an acid problem, right? So let's find an example like that. Is number 3 an example like that by any chance?
No, number 3 is calculating delta G.
Okay, so at this point we're actually not done. We also need to get 3x is equal to 18.6 times 10 to the minus 8 to get the hydroxide concentration as well. And now we're done with the problem. Should we take a sidestep and look at an acid problem where we've got something present? Where we've got like things on both sides of the reaction, the thing you're asking about? Does that sound good to everyone? Okay, let's do that. I got a lot of nods. No one yet shouted yes to that, but we got a lot of nods. Okay, so let's go ahead and, I'm going to get myself in trouble because I'm going to try to make up a problem. But let's make up a problem real quick. I'm going to erase this. We go with this? Okay. So let's make up a problem.
Do we ever do like ice tables with like half reaction stuff? Because I was just thinking of like...
You can't do ice tables with half reactions, but you can do ice tables with a full redox reaction.
But like, okay, yeah, because I was just thinking, because redox reactions, there's like stuff on the
Products and reactants on both sides. So let's go ahead, let's do like, acetic acid. I'm just going to do something simple. CH3COOH, aqueous NH2O goes to CH3COO minus, aqueous plus H plus, aqueous. If you want to write H3O plus, you're more scientifically correct, but I'm just going to leave it as H plus for now. We'll get into that next quarter again when we talk about the Bronsted-Lowry definition of acids and bases. We've got, let's make up some initial conditions. And let's say we've got, what's your favorite number?
3.
Let's say we've got 0.333 molarity acetic acid. What's your favorite number?
6.
Let's say we've got 0.600 molarity of acetate anion. Do we want all 3 things present? Let's start with just say that H plus is 0 molarity. Right, in this situation, my initial, where I would calculate my Q value, is going to be products over reactants. My Q would still be 0. Even though I've got reactants present, I would still say, oh, I have to make some amount of products because that 0 can't stay 0 if I'm going to hit equilibrium. Equilibrium constants are always bigger than 0. So my Q is 0, KEQ has to be bigger. I have to go towards products a little bit. But let's say, for fun, we've got some H plus concentration. I'm gonna do it kind of easy. Pick a number 1 through 5. Okay, so we're gonna say we've got 0.1, 2, 3, 4. We got 1 times 10 to the minus 5 molarity. It's a pH of 5, right? We've got some concentration of H plus there. Now, which way does the reaction go? Towards products, towards reactants? I can't tell. I can't tell looking at it. If I got all 3 things present, these 2 things could combine and go this way. This thing could fall apart more that way. I can't tell. So what I have to do is I have to do Q versus
Do we have a
KEQ.
given KEQ value?
The reason I picked acetic acid is because I know the KEQ is 1.8 times 10 to the minus 5.
So we do have it.
So we have a KEQ value. And now we can say, oh, in this situation, I know my KEQ value, my equilibrium constant is 1.8 times 10 to the minus 5. And my Q value, I like to, when I'm doing these checks, I put a question mark over it, because these things aren't actually equal. I'm kind of doing a logic check of how do these things relate to each other. I'm checking. And I'm gonna do 1 times 10 to the minus 5 times 0.6 divided by 0.333. And I'm gonna get some value. 6 divided by 0.333 times 1e minus 5. Oh, I did positive 5. 6 divided by 0.333 times 1e 5 minus. I'm going to get 1.8 times 10 to the minus 4. My Q value is bigger than my KEQ value. So in this situation, my reaction would actually go backwards from how it's written. My acetate ion and my hydronium, my H pluses, are going to react. This 0.333 should get bigger. These both should get a little bit smaller.
Because when Q is greater than K, it goes to react.
So then
Exactly.
your minus x's would be on the right side.
Yeah, so if I set up some change situation, there's two different ways we could do this. I could flip the reaction and use 1 over the Ka value, or you could do it where it's plus x, minus x, minus x, right? Flipped from what we've usually seen because I'm going in the backwards direction. Question?
The KEQ is greater than the KEQ is greater than the Q.
No, sorry. I've got, this is the KEQ.
Oh.
This is the Q. I have it written differently up here, but I like to do it here. Let's fix that. Right. I always like to do KEQ first, just so I have like a system.
So whenever like in the situation where there was no H plus, then it would always be that we're going towards products.
Yeah.
Okay.
Or if we had no acetate ion, right? If one of our reactants is if one of our products is 0, we have to go towards products, even if it's a tiny bit. Question here and then there.
So wait, if Q is bigger than KEQ, why is it going back towards reactant?
So if Q is bigger than KEQ, the way I think about this, I got a couple of tricks for it, right? The first thing is I've got I think about it just in terms of the numerator. Right? And essentially this is saying I've got too many products compared to my equilibrium, so my products have to go down. That's the kind of, I just do better just thinking about the numerators. So that's part of how I think about it. Also, if you do KEQ before Q, that less than sign makes a little arrow pointing the direction it goes. And so I'm like, oh, it goes that way. And that's why I always like to do KEQ first. It makes it so I don't, because otherwise I have to think through this every time. And so once I realized there was this little like visual trick I could do, it just saves me about 30 seconds every time I do the problem. Since I do these problems a lot, it saves me a lot of time. Question?
And if you were to do like an ice table for this, you would like set up KEQ equals the concentration of CH3COH over that, because your products and reactants flip.
Well, there's two different ways we can go about it. We can actually set up, so if we do the flip, then we have to do 1 over KEQ, we got to do our Q flipped, and we're going to have it go towards product still. If we do our change like we've got here in green, we could just do it where we have 1.8 times 10 to the minus 5 is equal to products over reactants 0.6 minus x times 1 times 10 to the minus 5 minus x divided by 0.333 plus x. And we can just solve this. Ooh, with a problem. Oh, this is gonna suck. What's the problem here? You can't do x as small. My Ka value is almost the same as my H plus value. X as small approximation is definitely gonna fail here. Question?
Could you not use the x as small approximation on the denominator?
You could, but if you're using, you could use the x as small in the denominator, you could use the x as small as here. So maybe you could simplify it some. I don't know if that would still.
So, like, if I were
That
to
might
solve
work.
this, okay.
That
So
might work.
if I were to solve it, then I just assumed x is small for the denominator, then I could multiply both sides by 0.33 and then distribute out and then solve for x.
I think we can actually partially use the x as small approximation here. I've never done a problem like this where you can partially use the x as small approximation. That, like, having all three things present is kind of a weird situation. But we can try this, right? So I can look at this. I'm going to switch colors, but I can say 1.8 times 10 to the minus 5 is approximately equal to 0.6 divided by 0.333 times 1 times 10 to the minus 5 minus x. I think the only place where the x is small approximation fails is there. But again, I've never done a problem. I don't know why. The number of years I've been doing this, I can't believe I've never done a problem where you can use the x is small approximation some of the time in a problem. It feels weird to me. Feels valid, but feels weird. Let me see what we get. 1.8 times 10 to the minus 5. Oops, 18. 1.8 times 10 minus 5 times 0.333 divided by 0.6. Negative plus 1. Huh. I don't know if that worked or if I just tried to do it in my calculator too fast. But I got x is equal to 1 times 10 to the minus 8. Which feels weird. I don't think it's worth it for me to. I'm really curious about this, but I don't think it's a good use of time.
So something like this wouldn't be on the exam where we have 3.
No.
Okay.
Right. It would be just this first part where I say in this setup would it go towards products or towards reactants. Wow. Okay. I think I'm doing it wrong, but in any case, or it's the x is small, like this kind of mixed x is small is not working. Something weird's going on. Should we keep going? So was that kind of the thing you were talking about?
Yeah.
Okay. Let's do quiz 3, number 3. Sorry, quiz 5, number 3.
Yeah.
Okay, if I erase all this? Okay. I think we're done with that part too.
Okay, calculate the value of delta G for this reaction at 25 degrees Celsius when the concentration of silver ions is 46.4
Hold on. Okay.
UM,
Micromolarity.
and the concentration of carbonate ions is 54.4 micromoles.
54.4?
Yeah, or 25.4, sorry.
Oh, okay.
My bad.
All good.
And the equation is AgT2 CO3 solid.
Wait, Ag2CO3
Yeah.
goes to Ag plus
Yeah.
plus CO3 2 minus.
And KEQ equals 8.1 times 10 to the negative 12th.
Right. Now it specifically asks for delta G, not delta G standard. So we're kind of back in time to the problem we did towards the beginning of office hours, where we're going to have delta G is equal to RT ln Q over KEQ, where we have to make sure we calculate Q and KEQ correctly. Just Q, we were given KEQ. So I'm going to go ahead and just plug things in. Delta G is equal to 8.314 times 25 degrees Celsius times 298 Kelvin times the natural log of my KEQ value. I can just write here 8.1 times 10 to the minus 12. My Q value is going to be just the products, really. So it's going to be carbonate concentration 2.25. 25.4 times 10 to the minus 6 times, those should be curved brackets now, times silver concentration 46.4 times 10 to the minus 6 squared. Because my Q value is going to be Ag plus squared times CO3 minus. I did it in the opposite order in there, but that's kind of what it's going to be equal to. So I have my silver concentration squared. I've got my carbonate concentration times that. I can already tell, well, this wants us to calculate the actual delta G value, but we got all the numbers in, now we just calculate. I can tell delta G is going to be negative in this case.
So when there's no what's it called, concentration on the left side, it would just be Q equals the reactants?
Well, because this is a solid. So, right, we don't include solids in our Q expression.
Yeah.
Right, that was part of the reason why I had to do an acid-base reaction to get the reactants on both sides, to get values on both sides. Because with the solid, we don't include those solids. The way we put it is those solids are not active in the solution. And we're looking for the things that are active in the solution. How they're bumping around in the solution, how they run into each other in the solution. That's where that equilibrium is happening. Scooch in, scooch in. Okay, that was number 3. I think that puts us on track to start talking about voltaic cells. Are there any other equilibrium questions, things from 7.1, 6.1, 6.2? Yeah.
Can I just pull up a question of like a drop down question?
Sure. Which one is it? Is it one that's already on the board?
I can.
Okay.
You can start.
Okay. So we'll start with that, and we can also do it. If it's one that we already did, I'll still do it with you, but I'll do it after I stop the recording.
Okay. Thank you.
So let's go ahead. Let's start looking at these electrolytic cells, voltaic cells. Right. So at this point, we use KSP values to talk about our precipitation reactions. We use Ka values to talk about our acid-base reactions. And then we wanted to start talking about our redox reactions. And it went really weird really fast. I think you can all agree to that, right? We put in a bunch of weird equations. It's like, why aren't we just doing delta H and delta S, delta G, and KEQ anymore? And that's because we can do really weird things with redox reactions. Essentially, historically speaking, physicists started studying voltaic cells and the generation of electricity from the combination of different elements in their solutions while chemists were simultaneously doing reduction oxidation reactions on the surface of materials to explain corrosion. And they were kind of working separate from each other. And so they developed 2 sets of language, 2 sets of the ways they talk about it, 2 sets of the ways that they were like quantifying it. And then they eventually talk to each other and they're like, we're doing the same thing. And then it's like, how do you do it when it's all the same thing? So let's talk about a little bit about what's going on with voltaic cells generally, and then we'll get into some of the specific problems. So generally what's going on with voltaic cells is still the same energetic considerations, right? We have some sort of delta G is equal to negative RT ln KEQ associated with it. And the problem is, when chemists were doing this, like I said, this is like what we did in 124. You put a stick of copper into a silver solution. Do you remember what happens when we do that? This was the 124 lab where you dropped a strip of copper, you dropped a copper wire into a solution.
Didn't it start to like form something?
It forms like fuzzies, right? It gets like some of the students say it looks like a Christmas tree, but it starts to form like a fuzzy thing on the surface. That fuzzy stuff on the surface is actually silver solid precipitating out. Because what's happening is a redox reaction of Ag plus Cu solid goes to Ag solid plus Cu2 plus. Do a little bit of charge balancing. So that chemical reaction is happening directly on the surface of the copper when we put it into the silver solution. So all I need present, I don't need these things, all I need is if I have those two things present, goes through a reduction oxidation reaction, makes these other compounds appear. Right? So that's what chemists were seeing happening. We're like, oh, this corrosion type process happens. Something acts as like, silver is, copper is getting oxidized. There's no oxygen in this case. That's the other unfortunate thing. All of the language around redox reactions was originally discussed in terms of oxygen's behavior. Here, we've got oxidation occurring where silver is acting like an oxidizing agent, right? It itself is getting reduced, copper is getting oxidized, silver is the oxidizing agent. Silver is getting reduced. And so we can talk about these reactions in terms of their delta H's, their delta S's, their delta G's, and their equilibrium constants, and we can do some equilibrium calculation on this from initial conditions. Same things we've been doing with all of our problems. But then the physics folks came by and said, you know what else you can do? We can take this setup, and because one thing's losing electrons, one thing's gaining electrons, we can set it up where I've got essentially a beaker. I still have that copper strip in there, but I stick it into a copper solution, and I get my other beaker, and I stick a silver strip into it, and I put it in a silver solution. Then I attach a wire between the two. And I'm essentially able to do the reduction half and the oxidation half at a distance. I can make half reaction happen over here, half reaction happen over here. As long as they're connected, through the solution and through the electrodes. We need a non-reactive salt bridge, and we need a non-reactive wire connection. If we have those two things, I can essentially do a copper to copper 2 plus reaction, and I can do a silver plus to silver solid reaction. And I can do those two reactions away from each other. This experimental setup is the reason we talk about half reactions. This experimental setup is why we talk about standard cell potentials. This experimental setup generates some energy from the way that the silver ions behave versus the copper. We can relate this back to 124 ideas, right? We can relate this back to ionization energy, electron affinity, electronegativity, and how that the silver ions are able to essentially create this force that pulls the electrons off of the copper. And we've got this nice conductive connection so that the electrons can flow all the way over and the electrons can be pulled off. We can also talk about it in terms of the KEQ, the delta H, the delta S. That would take all of those fundamental ideas into account. And we can also think about it in terms of some standard cell potential. Delta G naught equals NF E cell naught. Right? And this idea of standard cell potential, again, comes from the physics folks. The idea of equilibrium constant comes from the chemistry folks. And it was only really, and chemistry folks got some stuff right, physics folks got some stuff right, but it was only when they started talking to each other that we get the modern creation of the batteries that we see today, and like actually being able to make like lead acid batteries, lithium ion batteries. There's some really cool lightweight batteries that are like silver oxide batteries. They're really expensive, but they have like a 200-year shelf life. So I've done problems in the past where you just look at the behavior of silver oxide batteries. They're not very common. They're used in some ballistic missile devices, particularly like nuclear weapons. These things where it's like, it needs a battery, but we only need to use the battery once, and we want it to be still working in 200 years. And so these silver oxide batteries are these incredibly shelf-stable batteries where you essentially crack open a thing of, like there's a little like charge that pops an oxygen thing, battery suddenly reacts, and you get this huge voltage shot out. And they weigh very little because you just need a piece of metal and oxygen gas separated from each other and then mixed. All kinds of crazy things you can do. But what we can see here is this standard cell potential is not actually doing anything different than what we've been doing. When I relate that delta G equation on top to this delta G equation on bottom, I can get my natural log of the equilibrium constant is equal to NF. Oh, I forgot a negative sign here. Sorry. That's supposed to be negative NF E cell. NF over RT E cell. We talked about this in class yesterday as well, right? My standard cell potential is, it's not linearly proportional, it's natural log proportional, but my standard cell potential is directly related to my equilibrium constant. So standard cell potential, splitting up into half reactions, is just another way to talk about the equilibrium phenomena. But it talks about the equilibrium phenomena in terms of the energy I can get out to run some device in between where the oxidation and reduction are happening. What chemists did originally, where we just saw corrosion happening, you don't get any useful electricity out of that. But when we split it up into two halves like this, there's other ways you can do it, but splitting up to two halves is the common way. You can also make a galvanic pile. That's like the historic, like first battery that was ever made. You can get some useful electricity. Historically, there's some really interesting debates going on about when the first battery was actually made, because there's evidence that that somebody in ancient Egypt actually made a vinegar battery. Like they found this weird jar that was like a double jar that had chunks of metal in it, and they're like, we have no idea what this is for. But a couple of chemists and physicists looked at it and said, hey, you could make a battery with that. And so there's debates about like, were they actually getting like essentially electric shock bulbs? So like from the setup they saw, you'd essentially just have two prongs and you can like shock somebody with it. It's like a big jug you have to carry around, but it's a little like taser. And if you connect it, it shocks you. Under debate, as far as I know, I haven't looked into it. I saw the reports on that probably about a year and a half, 2 years ago. I don't know if that debate has been settled or not, but there's evidence that even in ancient Egypt, they were playing with some of these battery ideas. So, pretty neat. Still an equilibrium idea. It's things that we've been trying to understand better and better for potentially centuries. We can also do non-standard cell potentials. That's where you use delta G instead of delta G naught. And that's where you get to the Nernst equation. Without going through the full derivation, you get E cell is equal to E cell naught minus RT over NF ln of Q. Where my standard cell potential is essentially taking care of my equilibrium constant. And then this RT NF ln Q is taking care of how I'm varying from standard conditions.
I think in class you used like some examples where you made E cell not 0 in certain cases.
Yes.
And what were I was confused on what those cases were.
So those are cases, it turns out, so this is what we usually think about when we think about batteries. We think about an anode and a cathode. We think about like two different metals or two different things, one thing being oxidized, one thing being reduced. But there's this really common type of battery that nature has made already. And nature has been making this battery since first life appeared, right? Anything like, pretty much everything that's alive, plants, bugs, humans, dinosaurs when they were around, we work off of electrical currents, right? Our neurons are electrical firing systems. How do we get electricity inside of us? And some of it can be through redox reactions, but you can also set up this weird situation called the concentration cell. Well, let's not do it over, let's just do a different one. So we can set up this situation where I can, and I wrote down this silly reaction before. Right, this is Ag plus, this is also Ag plus, this is an Ag electrode, this is also an Ag electrode. We connect it with a wire. Now, if I did anode, is there any electric potential difference between silver ions and silver ions? No, they're the same thing. That would have no standard cell potential. E cell not, the standard cell potential would be 0. But if I tweak these concentrations, let me think about this real quick. If I made this one approximately 0.001 molarity, and this one let's say 3.33 molarity, having a difference in concentration is essentially going to pull electrons over towards the cathode. Because there's more ions there. Now we've set up this kind of this ion imbalance, and now we can have electrons get pulled across. So even with the same two compounds, if they're set up, we do need that salt bridge connection still. We need a non-reactive salt bridge. If we set this up, we can create some voltaic potential just by having a difference in concentration. Our cells do that all the time.
Okay, so that's when you have the same solution on both ends.
Yeah.
But the change in concentration just affects your reaction quotient.
Yeah.
Okay.
So we changed the Q. E cell, the equilibrium value would be 1. So our E cell standard, right? Natural log of 1 is 0, so 0 cell standard. It's just the Q. Question?
Is anything about buffers gonna be passed on the exam?
A little bit would be fair, right? Where buffers is just that common ion effect of acids. Oh yeah. How much do you remember?
All I know is buffers, if you add a little bit of acid or base, it doesn't change the pH.
Okay. And then did you have a question about this problem?
Yeah, she.
Oh, she asked it. Okay. So, let's go ahead. Let's talk about buffers a little bit. We were going to start talking about cell potentials, but we can go back a little bit and talk about buffers. That's fine. Does everyone want to hear that little bit? Okay. Again, a lot of nods. So, from this point, with these kind of these 3 equations on the bottom here, we can do pretty much everything that we need to do with cell potential. I guess there's one more that we should write down, and that is E cell standard is equal to E cat minus E an. Where the cathode, a lot of people got confused by this last night in class, the cathode is referring to this entire experimental setup on this half. The electrode, the solution, everything. Sorry, that's the anode. Ooh, the anode's this half. The cathode is this half, and it's the electrode, the solution, everything. Right, so in that corrosions lab, we saw the iron nail in the cathode, but not participating in the redox reaction. It was just an electrode that was transferring, that was just a surface for electrons to hop off of. But it was still part of the cathode, because the cathode is the entire experimental setup. So, cathode and anode is the experimental setup. Reduction half, oxidation half, that's the kind of chemical setup. Okay. How are we doing on time? Ooh, not much. Okay, so let's talk a little bit about the common ion effect and how that, the language we can use or avoid around the idea of buffers. I'm going to erase all of this. I'm going to leave this stuff at the bottom because I think that's going to be useful for the next set of problems we do. Right, so we first saw the common ion effect with something like Let's do the silver carbonate example again. Ooh. Right? So if we were going to 2Ag plus aqueous plus CO3 2 minus aqueous, if we were doing this not into water, but we were doing it into a carbonate solution, that's where we get like 0.222 molarity, right? We've got some molarity of carbonate already present. Common ion effect, right? I mix sodium carbonate and silver carbonate together. I don't write them both as reactants. The ion they have in common is carbonate. Carbonate just acts like a product that's already present. And that's going to affect my equilibrium, because now when I do KQ, I do my initial change equilibrium, like it affects everything. We see this also when we look at acid solutions with their Kas. Let's do carbonic acid. So if we looked at carbonic acid, well, I want to pick something else. I don't want to have too many carbonates there. Let's do oxalic acid. Right, so oxalic acid will dissociate into HC2O4 minus and H plus. Right, in this situation, I'm going to have some initial concentration here, right? And if I had zeros, if it was just oxalic acid into water, these would be zeros, and I'd go that direction, something would happen. That would not be a buffer, that would just be a weak acid in solution. If I had the common ion effect for a weak acid, that's a buffer, right? So common ion effect for a weak acid would say, what if there was also some of this present? Right? If that is also present, we're going to say H plus is 0. Right? If both of these things are present, I've done this situation where now I've got weak acid and something, and its common and its conjugate compound present. It's weak acid with its common ion. Both those things present. This thing could take the H plus and go this way. This thing could give up the H plus and go that way. So I've got something that's going to kind of balance out giving H pluses and taking H pluses. So it's going to balance the pH and how much H plus is present. If I start to remove the H pluses, this falls apart more and kind of balances it out. If I do something where I increase the H pluses, this reacts this way and balances it back out. Question?
So the H plus is 0. Would it just take H's from the water?
No, it would actually be this thing falling apart.
Okay.
This thing would fall apart to get to equilibrium. And then once we get to equilibrium, so we can calculate the equilibrium values. Right, I'm going to have minus x plus x plus x. I'm going to have approximately 0.777. I'm going to have approximately 0.111. And then I'm going to calculate my x value. Oh, shoot.
Minus x and plus x included in that equilibrium?
What's that?
Like, is minus x in like 0.77 minus x is not included, like the x isn't included?
So I'm doing approximate or using the x is small approximation already.
Okay.
Can you hand me one of those equation sheets? Yeah. Thank you. I need the Ka value for oxalic acid. I don't have it memorized. There it is, 5.67. Ooh. Whoops. The reason I just made a face is because with that Ka value, maybe the x is small approximation is bad. So let's go ahead and calculate it, and we'll go ahead and see if the x is small approximation is bad or not bad. So I'm going to go ahead and do 5.6 times 10 to the minus 2 approximately times 0.777 divided by 0.111. X is small approximation fails. I should have looked at the Ka values before I pulled it. So in this situation, X is small approximation is going to fail. Let me put it out a little bit more explicitly. I picked an acid for the Ka value was too big, so I picked a bad example. This is why it's hard to make, dangerous to make problems on the spot. So technically, let's go ahead and include this minus X plus X, right? My Ka value would be, oh, that's not 0, that's x. My Ka value would be x times 0.111 plus x divided by 0.777 minus x. And I would say that goes to Ka is approximately equal to x times 0.111 divided by 0.777. And that would get me the x is equal to 0.39. So my concentrations were too small compared to my Ka value. I can tell my x value is bigger than my initial concentration. X is small, fails. So I made a bad example on the spot. X is small, approximation fails. But we can see, it's still going to go forward some, just not as much as I'm predicting. Predicting that x value should be smaller than I wrote. But I'm going to get some equilibrium H plus concentration there. Now, if I dumped acid on top of it and I increase that H plus, Le Chatelier's principle would say, oh, that's going to push back towards reactants. If I add some OH minus to remove that H plus, remove the H plus, then it's going to push back towards products. But I've got a system that can push back and forth and essentially keep the pH around the same value. And that's what a buffer is. It's the weak acid common ion effect. Bad example, though. X is, well, great example for a buffer, bad example for X is small approximation. Questions about that, or should we get back to some electrochem? Okay, we don't have a ton of time left. I'm going to go ahead and erase all of this stuff. We got a lot to do still. So, I guess let's just keep going. 7.1, number 18. Who wanted that one?
I didn't, but my computer died, so I
Oh
can't.
no! Can someone pull up 7.1, number 18?
It's a bit misleading to say that no reaction occurs based on E cell in the same way that delta G only determines whether a reaction is product favored or reactant favored at equilibrium, and not whether the reaction is spontaneous. We often say no reaction occurs because equilibrium lies so far towards the reactants. If E cell for a 1 electron transfer is negative 1 volts, what is K for this reaction? Assume 25 degrees Celsius. What does
E cell or E cell standard?
Oh, sorry, E cell standard. What does this tell you about the amount of products that will be produced at equilibrium?
Okay, so if we have an E cell standard of 1 volt, we can kind of just plug it in to either of these and find the KEQ. So we can plug it into either of these and we can find the, we can find the delta G standard, we can find the KEQ, we can figure out whether this is going to be product favored or reactant favored. So I can already tell with a negative voltage that it's going to be reactant favored. Right, so if we look at a 1 electron system, let's do something zany. Let's say we've got lithium plus Ag plus goes to Ag plus lithium. That's a terrible example. That's not going to be negative 1 volt. Again, trouble with making examples on the spot. Let's do this. Do I have a 1 electron? Let's see. That's 2 electrons. 2 electrons. Oh, it's really hard to find 1 electron examples. 2 electrons, 2 electrons. Very few things only do 1 electron. 2 electrons, 2 electrons. There we go. Oh, that's a bad example. That one kind of works. Okay. I can't find one that's going to do 1 volt, but I want to get something that's a negative voltage. I can't find something that's going to be 1 volt and 1 electron, but we can calculate. It doesn't matter. I'm not going to be able to make an example on the spot. But we can still calculate, was it asking for KEQ or delta G?
What is K for this reaction?
So we can essentially just use this equation. We can do 1 times 96485 divided by 8.314 times 298 times -1, all to the power of E is equal to K. Right, I'm using E to get rid of the natural log. I can plug all of that in, I can get a K value. I'm going to have 1 times 96485. Well, that's equal to 96485, go figure. 8.314 divided by 298, negative to the power of E. And I'm going to get K is equal to 1.22 times 10 to the minus 17. Right, so when we look at this, and this is where we say, right, everything we said, oh, cell potentials, it tells us spontaneous, non-spontaneous, towards products, towards reactants. We never see negative cell potentials. Right, really, the reason we never see negative cell potentials for a reduction-oxidation reaction is because when I mix the two things together, it is so reactant-favored that, like, the reaction's over in like a flash of a second, and we see nothing happening afterwards. So technically some amount of reaction happens, but we're looking at like trillions of times more reactants than products. So you only make the smallest amount of products. You're going to only get like a few electrons transferred before you reach equilibrium. So in terms of a practical voltaic cell we would use, this would be not practical. Right? It just wouldn't really do anything interesting. Also notice that even with a -1 volt, our equilibrium constant is pretty massive. If that was a positive one, let's compare to a positive 1 volt. Okay? So let's say, what if it was right? Why is it so impressive to do it for positive 1 volt? The only difference is I'm going to do this, E is going to be to the positive of this. So I can go ahead and take the natural log of that, take off the negative sign, do E to that, and I'm going to get, for a positive cell potential, I'm going to get my K value, my KEQ value, is equal to 8.18 times 10 to the 16. So this reaction is going to happen billions and billions of times more than this reaction. Right? If you look at the difference there, that's a factor of 31. I don't even know how many zeros that is. I mean, I know exactly how many zeros that is, but I don't know what you call that, like trillion times. Right? So when I'm looking at this reaction happening backwards versus forwards, essentially the positive voltage version versus the negative voltage version, the positive voltage version is going to run for a really long time. The negative voltage version is going to run out immediately. Now, where this is important and interesting is when we start to think about the Q value. What's actually present to react? What's our non-standard conditions? So if we had a setup, I don't want to do that. I'm going to do a +2, so it's going to be a little bit different. But let's say I had tin 2 plus nickel going to nickel 2 plus tin. This reaction would have a standard cell potential of 0.12 volts. Right? So if I had tin present, but remember, that's telling my KEQ, not my Q value. Right? And if I set this up where I'm like 1 molarity, then that's going to be my cell potential. Right? But if I set it up so it's 0 molarity, 1 molarity.
That's actually the problem that I asked for number 8.1 is array of different molarities.
Okay, we can look at that, but I'm doing a kind of extreme version. If we have 0 molarity, if we don't have any tin ions, can this reaction even go forward?
No.
Can't even go forward. It has to go backwards. How much backwards? Very, very, very small amount backwards. But it has to go backwards a little bit. So we will see in that case a little like negative voltage flash, but then it's going to hit equilibrium really quick. So we have to look at, if we want to figure out why those like negative voltages happen, we have to look at Q versus KEQ, E cell versus E cell standard. Where are we versus where we're going? Now, if I wanted to set up the equilibrium values of this, like where do these concentrations end up, this thing is going to be close to 0, but it's not going to be 0. This thing is going to be close to 2, but it's not going to be like 1.99999999999999992. Right? I didn't say enough 9s because it's got to be like 17 9s. But it's going to be very close to completely reacted. So this is going to end up approximately 0. It's not actually 0, but it's going to get to approximately 0 eventually. So if I do initial change equilibrium, that'll end up being approximately 0, but not exactly. And we can't solve for exactly how much it would be. That's getting towards this idea of like doing diverse reaction calculations. That's again getting towards some third quarter chemistry stuff where we spend a lot of time on equilibrium calculations going forward and backwards. Since we're on the topic, should we look at 8.1 number 13? Non-standard cell potential? Okay. Let's look at 8.1 number 13 real quick and see how it plays into this idea as well. See you back, see ya.
So consider this cell Fe solid, Fe2 plus aqueous, and then the other one is Ag plus, but it's like anode cathode notation.
Oh.
Ag plus aqueous and Ag solid.
Okay.
And then suppose that we run this cell for a long time until the system reaches equilibrium. What is the cell potential E cell at this point? What is the standard cell potential E cell at this point? And then it asks like 3 drop-down questions.
Does it give us does it tell us anything else about how long we run it for?
It says until the system reaches equilibrium.
Oh, until the system reaches equilibrium. Okay.
Yeah. And then, okay, so is the cell potential affected by adding more Fe solid?
Well, hold on. Let's do one part at a time. The drop-down menus take more thinking.
Yeah.
See you guys. It'll also be recorded if you want to see the end of this one. Okay, so if we're at equilibrium,
E cell is 0. Right?
E cell is 0.
It's like the same way where like when you're at equilibrium, then
Delta G is 0, right?
Yeah.
And we can do delta G equals negative NF E cell, right? Non-standard, non-standard. At equilibrium, delta G is 0, so E cell is 0. Cool. Okay. So we know that E cell is 0. What about the standard cell potential?
You can use the stuff in the back, but first write out the.
Don't even need to, right?
Cathode minus anode.
Let's do cathode minus anode. 0.8 minus negative 0.4 is going to be 1.2 volts.
Yeah.
Right. Equilibrium doesn't affect the standard, like what our standard cell potential would be. Our non-standard cell potential is 0 at equilibrium, but there's still some standard we can refer to.
And then, so the.
Now let's do the drop-down menus.
So is the cell potential affected by adding more Fe solid? I know that should be no, right?
No, right?
Yeah.
So adding Fe solid, right? Let's go ahead and write out the balanced chemical reaction. Think about what the Q expression is and the KEQ expression. So I'm going to have Fe plus 2 Ag plus goes to Ag solid plus Fu up to Ag plus Fe2 plus. My Q expression is going to be products over reactants. It's going to be Fe2 plus divided by Ag plus squared. right? And so when we're doing these drop-down menus, we're really doing Le Chatelier's principle again. I'm at some equilibrium. I'm disturbing that equilibrium. How does the system respond to that disturbance? So we add solid iron. Does that affect my Q?
No.
Nope, no effect.
And then the other one is adding more Ag plus. So
Adding
it
more
decreases
Ag
the Q,
plus
right?
is going to make the Q smaller.
Yeah.
If the Q is smaller, then we've got to go back towards products more.
And then this was the thing I was asking you, is like, is the cell potential affected by letting half of the water in each of the cells evaporate?
Okay, so this is kind of a funny one. So this is kind of a real issue with, I don't know if it's a real issue, we use sealed batteries these days. But if there's evaporation, this gets back to that whole concentration thing, right?
Yeah.
So let's say it evaporates. Let's say we're at, we've hit equilibrium. Let's say they're at 0.2 molarity, right? So at equilibrium, we've got 0.2 molarity here. We've got 0.2 molarity here.
So
Right.
if you evaporate half, then you'll have like.
Right. This silver getting more concentrated is going to have a bigger effect.
It's gonna make the Q bigger, right?
Um,
Because it's 0.2 divided by 2 squared.
oh yeah.
And then, so that's a smaller number on the bottom.
Yep. So Q's going to get bigger.
But it's so I'm not sure why it's wrong.
Let me see. Okay, the cell potential half the water. The cell potential increases. So if Q, wait, which way is Q going in this case?
Q is increasing. If you have the.
Not half, double,
Oh,
right? Because
Oh,
we're
yeah, if you
increasing the
double it.
concentration.
but that's
So if
still
we
a
double the
decimal, though.
concentration, what's that?
It's still a decimal though. So then and then you square that decimal, the bottom
Okay.
would be smaller, right? Because 0.2 times 2 is 0.4.
Okay.
And then 0.4 squared is a smaller decimal, isn't it?
Okay.
0.1.
So Q is going to, oh no, that's great, right? Because then we're going to be subtracting a smaller value off. So
yeah.
cell potential goes up because we're subtracting a smaller value off, right? Because
Yeah.
we're subtracting that.
Yeah, that's what I.
Oh, saying in.
So the cell potential would increase, right? That's what I was saying.
Um,
Or would it be that because it's a natural log of a Q that's between 0 and 1, so that would give you a negative number, so actually. Wait, no, yeah, that's what you were just saying, it would increase.
Let's see, which one is it supposed to be? Well, that's not the one you have wrong.
Well, then I don't know.
Okay, so
Because we went through
that's a
Yeah.
specific thing. I'm gonna have to look at your work to figure out. But
Okay.
like, I agree that the cell potential should be increasing. I just did a quick check
I
to
think
see.
it's just the 3 that we just went through. One of those has to be wrong, but I don't know what.
Okay, well, let's see. Let me take a look at it more specifically. Okay, is the cell potential affected by that? Is the cell potential affected by adding more Ag plus? Adding more Ag plus should, oh, you put yes decreases instead of yes increases for the Ag plus.
Oh.
So, yeah, no, adding Ag plus, you're adding reactants, so it should make the cell potential. Again, and I think I know where I think I misspoke earlier because that Q value is getting smaller. So I changed the last one around though, so it fixed the last one.
Oh, okay, the last one should be that it increases.
I believe so.
It's okay, we can do
Here.
some other time because everybody else has questions.
Well, office hours are over now, so.